With that, I'd like to introduce our speaker. We're very happy to have Professor Andrew Gelman join us today. Professor Gelman received his undergraduate degrees in mathematics and physics from MIT, and he subsequently completed master's and PhDs in statistics from Harvard. He is the Higgins Professor of Statistics at Columbia University and a very busy person. He's the founding director of the Applied Statistics Center and the Quantitative Methods and Social Sciences program, both at Columbia, while having joint appointments within Columbia and also external to Columbia. Professor Gelman has a long list of very prestigious awards, including membership in the American Academy of Arts and Sciences. His 8 books and numerous journal articles and great software, free software, including Stan, have all been very influential. But Professor Gelman's professional work and interdisciplinary outreach offer him a unique vantage point for discussing timely issues of interest to our applied math community. And so we're delighted to have Andrew Gelman as our CAM Colloquium speaker today. And with that, I would just turn things over to Professor Gelman.
Okay, thank you. It's a pleasure to speak at Cornell. My mother was a student at Cornell in the 1940s, and she took a class from Professor Feller. I asked her about it, and she said she couldn't really follow a word that he was saying. But it was, anyway, so it's a privilege to speak with you all. It's the Applied Math Seminar, so I want to kind of like talk about some mathy things or somewhat mathy things, and then some other issues about communication and statistical workflow. And I think we'll have extra time, which means people can answer questions or give objections and so forth. So maybe right now you can just when you're listening, you can scrawl on a sheet of paper what questions or comments you might have, since I think there will be a chance to do that. So election forecasting, I got into election forecasting decades ago. A colleague and I were writing a paper in around 1990. Actually, we started the project in 1988 when we were following the presidential elections. And Mike Dukakis, the Democratic nominee, was leading in the polls, but my political scientist colleague told me that it was that George H.W. Bush was going to win. And I said, why? And he said, well, there was a book written a few years ago by this guy, Stephen Rosenstone, a political scientist, who's called Forecasting Presidential Elections. And you can pretty much forecast elections from the economy. And the economy is going pretty well, so the incumbent party is probably going to win. And there are some numbers attached to that, and there have been some other research, which got us interested in the question of why the polls vary so much if the election is so predictable. The polls don't fluctuate so much as they used to, but back in the 80s, they were jumping around a lot during the campaign. It was somewhat of a paradox. If you can predict the election and you kind of know how people are going to vote, how come they don't know how they're going to vote themselves? So what's the role of the campaign? It appears that the role of the presidential election campaign is to kind of remind people who they were going to vote for already. Let me stress that this applies to US presidential general election campaigns. General elections for president does not apply to primary elections. It doesn't apply to elections in other countries and other offices. The general election for president is unusual among elections in that it has 2 stable parties, generally only 2 major candidates. So there's no strategic voting involved. You don't have to worry about throwing away your vote. You have months to decide who you're going to vote for. The party queues are very strong, and the 2 candidates have roughly equal resources, which isn't true in other elections. Anyway, 1988 passed, and so did 1988 passed, and so did 1989, and so did 1990. And it was 1992 when we were completing our paper. And we thought if we're really going to write a paper on how elections, why are polls so variable, given that elections can be forecast ahead of time, we should probably forecast the 1992 election ahead of time. So we took the standard models out there and put in some hierarchical modeling allowing state, national, and regional error terms, and we forecast the 1992 election. This did not use poll data, by the way. It wasn't poll aggregation. It was just forecasting based on economic fundamentals and previous election results. So having done that, we had a probabilistic forecast, which wasn't perfect. It had certain systematic errors of the sort that could be resolved from polls. But it gave us probability of Democrats and Republicans winning any state, and the probability of things like an exact tie in the Electoral College and other things. Nobody was interested in this. Election forecast, just nobody really cared about election forecasting. It was like a really backwater of political science. Then there were some economists who did it, some historians. Like there were people who did it, like these election forecasters, but it was not of general interest. Then a few decades later, it did start to become popular in the news media. And then this year, I was contacted by a data journalist from The Economist, and he asked me to help him set up a forecasting model, which we did. And I can, let's see, let me share it for you so you can see it. Give me a moment. Yeah, so here, a sec. Screen. Yeah, so there it is, The Economist forecasting the election. We say that Joe Biden has around a 86% chance of winning the Electoral College. We have these pretty pictures. I like to focus on the popular vote, so let me scroll down here. So we predict that we think that right now Biden has about 54% of the two-part support if the election were held today, 54% of the support the two-party vote, and we forecast he'll get about 53% on election day. So let's, okay. So where does that come from? Anyway, that's kind of all background. I'll first talk about the information that goes into the forecast, then the models and the assumptions we used, how we computed it, and how we summarized the results. So the information, we have national economic conditions and political conditions. We have previous election results in states. We have national polls, and we have state polls. So that's the information that goes into our forecast. How do we put it together? So it's kind of pretty clear. So state polls and national polls give us estimates, snapshots of public opinion. So our model is that a poll gives you an estimate of national and state opinion with two sources of error, sampling error and non-sampling error. And the sampling error is from standard formulas, from survey errors. The non-sampling error is estimated from historical analysis, which suggests that non-sampling error and sampling error are about equal. That is past, let me say, yeah, roughly speaking, the amount of error, sorry, I'm kind of babbling here. The source non-sampling error represents several different things. It represents that people's survey responses might not be accurate. It represents differential non-response. So the survey might have more Democrats or more Republicans answering the survey. It also has to do with who responds. So maybe you're doing this the time of day, the day of the week, all sorts of idiosyncratic features of the sample. some of the polls that we analyze adjust for party identification and some don't. So it's better if your survey adjusts for party identification. So if your sample has too many Democrats or too many Republicans, you can adjust for that. And amazingly enough, like, you can adjust for it. Often it's commonplace that you'll see a survey and it gives an unusual result, and then someone will look into the crosstabs and say, oh, that was the poll that had Donald Trump with 50% approval. That survey also had 6% more Republicans than any other survey would have. So you can do that adjustment. We do not have the raw data for most of the surveys, but we do know what they did. So our model is that there's a source of bias, that surveys that don't adjust for party ID have a bias, and that bias itself is a time series that varies over time. And this is from what we know from historical elections, that when candidates do better in some polls, that's typically because those polls have too many of one type of voter or another. In addition, different survey organizations have different potential biases. So the point is that we have a sampling and model of sampling and non-sampling error that maps polls to public opinion on that day. Then we have a fundamentals model which predicts the election outcome on election day based on the state of the economy, presidential approval, some other factors. That model recognizes that political polarization is increased. So the predictive power of the economy is less than it used to be. A strong economy helps the incumbent president, and a weak economy hurts the incumbent president, but less than in the past. So those are the two parts, the two data sources. A key part of the model then is to connect those two. So we connect the poll data to the fundamentals data with a time series model of how the multivariate, there's a 50 dimension, there's a vector of length 50 or 51 if you count Washington, DC. Let's say a vector of length 50, which is public opinion over time. They're 50 parallel time series. So we have a model for how that time series behaves. It's actually just a simple random walk model with correlations. The random walk model we calibrated based on the idea that public opinion actually varies slowly, but the relative positions of the 50 states can change from one election to the next. So states can drift towards one party or another. We have an estimate of how much they could drift in the 100 days before the election, and then you divide that by 10 to get the standard deviation for one day of the random walk, because of the variance of the random walk increases like the square root of the number of the length of the time series. So that's it. Now I will say this is different than other election forecasting models, perhaps, in the sense that we have a model for the latent process. I wouldn't say that makes it better or worse than other models, but it's different. So probably the usual way that you would see a forecast in the news media would be as a poll aggregation. So people say we have a bunch of polls, so we have a time series, but then it can be noisy, so we do some sort of moving average, and then some survey organizations are worse than others, so we downweight them, and then maybe there's some biases, and then we add error, then we add variance because it could be wrong. And so those poll aggregation methods are based on starting with averages and then kind of adding error terms to capture additional uncertainties. We're doing it in a kind of more statistical way. Let's wait till this ends here. Okay. Okay, thank you. Yeah, so and this there's kind of two different ways in some way of creating a forecast. And one way is what we're doing, which is to create a statistical model with 50 latent parameters that vary over time and estimate them all. The other approach is to kind of come up with a procedure and produce a forecast from the data and then try to kind of evaluate it and make sure it works okay. And those are just like different ways of going about it. So then, if you think of there being different forecasts that exist, the next question is, oh, shoot, sorry. Before I wanted to talk about calibration of forecasts, which is, I don't have a lot, it's kind of a pessimistic thing that I'm going to say next, but first I'll take the actual algorithm. So we're fitting a statistical model which has thousands of parameters because it has 50 states. It has for 50 states for every day during the election campaign, the public opinion about the state. So that's like, I don't know, 5,000 parameters, like 50 states in roughly 100 days. Mathematically, we have a 5,000-ish dimensional posterior distribution that we want to sample from. So we use Hamiltonian Monte Carlo, which is a physics-derived algorithm that moves through this 500-dimensional space. And we have to, so we fit it in Stan, which is our open source Bayesian inference engine. I think it takes maybe 20 minutes or so to run. It's not too bad. So every time we get a new poll, we rerun it. It was constructed by my colleague at The Economist, Elliot Morris, and also Merlin Heidemann's a PhD student in political science at Columbia, as well as by me. Before releasing the model, we ran it on 2008 and 2012 and 2016. So when you run it on 2016, it said that Hillary Clinton had a 2/3 chance of winning the Electoral College. And of course, she didn't win the Electoral College, but I don't know that a 2/3 chance of winning is so wrong. Like in some ways, she got a little bit of bad luck. It was, if we had done our model in 2016, we probably would have done worse. Like what happens is 2016 made us very aware of non-sampling error. So before, in 2016 and before, when people are doing poll aggregation, they kind of knew in the back of their mind about non-sampling error, but they didn't think that hard about it. But in 2020, we know that there have been serious non-sampling errors. So that's part of our model. So we get a certain correlated uncertainty from that. So the results from the previous elections kind of made sense. We did a lot of debugging that way. Once the model was released, people commented, it's like maybe a few weeks after it came out, some people were reacting to it. And one thing we said that, I think we had Biden with a 99% chance of winning the national vote. That is 99% chance that you would win more votes than Trump. And I don't know, like we felt 99% seemed too high. Like Biden's in the lead. I'm pretty sure he's going to win the election. We're not addressing things like the US mail destroying ballots or stuff like that. I'm talking here about vote intention, which is what polls are about. So I'm saying that I expect that more people will go and vote for Biden than will go and vote for Trump. But we didn't feel 99% sure. Now, I don't know, that's sort of, what do we feel like is kind of not the most meaningful thing, but it was enough to motivate us to go back and look at our model more carefully. And we found, well, first we found some actual bugs in our code. And then beyond bugs, we did not like how we had parameterized the correlations between the states in a random walk. And in particular, I think our correlations were too low. So what happens is if you have state level uncertainties and the state by state correlations are too low, then when you average over the 50 states, your estimate for the national vote becomes the variance becomes too small because you're averaging 50 independent things, or not independent, but correlations are too low. So by increasing the correlations, that increased our national variation. And then we ended up with Biden only having, I think it was like a 97% chance of winning the popular vote, which seemed more reasonable to me. I'm giving you this story because I think a lot of statistical workflow and I guess applied math workflow has this characteristic of like going back and forth between what information is in your analysis and what other information you have available. I wouldn't say that like the model predicted 99% and we didn't quite believe it. That wouldn't have been enough for us to abandon our model, but that was enough to make us look into the model and see problems with it and fix it. So I will say that I'm always a little suspicious. Like if you criticize someone's model and their response is no, we're right, I'm always a little bit suspicious, like because we all make mistakes. So like we should be like it's not enough of a defense to say like I did it, you know, like we have to recognize. So in science, we can all learn from our mistakes, but only if we're willing to learn, only if we're willing to accept that we might be wrong. Now, when different people do different forecasts, how do you compare them? So let me just give you a couple of examples. I'll share again our forecast here. Okay. Let me just, here it is, okay. Okay, so we think that Biden is going to get between 231 to 213 to 421 electoral votes. I think, as I said, I can understand this best looking at the popular vote, the national vote. We think that Biden is this is a 95% interval here for his share of the two-party vote. And so we think he's going to get between 50% and 57.5% of the two-party vote, roughly, when the election comes. Due to the distribution, as you might have heard, due to the distribution of the votes in states, Biden will need something like 51.5% of the vote to win in the Electoral College, which is this kind of weird thing that we don't want to think too much about. Here I'm focusing more on uncertainty in the prediction, so I'm not really going to talk about that particularly issue. Now, how do we evaluate a forecast? Like, how do we say whether we believe this? So when I see this 53.4%, where is it coming from? Well, if you see this graph, these are all the, do you see the little dots? Those are all the national polls. And so you can see, well, Biden's share of the two-party vote in the national polls is there, like around 54%. Separately, we have a fundamentals-based forecast, and that forecast estimates him getting about 53% of the two-party vote based on the poor economy and the low approval of the current president. Now we could look here. Let me give you another forecast here. So there's also a forecast from 538.com, which is a popular journalistic election forecast. Here they have Biden as favored to win the election. Well, they have Biden with a 77% chance of winning the election, which is, I think we have 87%. That's pretty close. I can compare it. Here is their popular vote forecast. Well, they don't actually here. It's slightly different than ours here. I'll kind of go back and forth. So we have an estimate that Biden has 54% of support right now, and we have an election day forecast of 53%. Really, you should focus on the election day forecast, 53.4%. Their election day forecast is 52.8%. So it's not that different. In some sense, like not only is it not that different, how could you ever really distinguish between 52.8 and 53.4? They're quite close. there'd be no, it's hard to pick between them. So this also is characteristic of a lot of like applied math projects, that you have a result, or maybe you have two different estimates. You can evaluate them based on their product, but ultimately you have to evaluate them based on what went into them. So you can't really treat the forecast as a black box, at least not if you have more than one forecast. Now we could also go to individual states. So let's go like here, let's go to, well, Alabama, that's the very first state here. Trump is supposed to win in Alabama. Here we estimate he has an over 99% chance of winning. Where's the vote? Okay, so we think Trump is going to get 61% of the vote in Alabama, but it's going to be somewhere between 55% and 66% roughly. So this is our range. Now let's look at their 538.com. Let me go to Alabama. Choose a state. There's Alabama. Here. Well, they think a plus 40 popular vote margin, that would be 70% for, so they think that Biden could win Alabama, that he could get as much as 52% of the vote in Alabama, or that Trump could get 70%. So their range is roughly 50% to 70%. So if you sort of go back, now this is the point I want to make. Here's our interval, our 95% interval, roughly 55 to 65. Theirs is roughly 50 to 70. How can you evaluate them given that there's only one election? I really think it's ridiculous to say that Biden might win Alabama, or that Biden might get 50% of the vote in Alabama. We could, but what can you do? Well, so one thing you can do is after you've made forecasts, you can calibrate them. So calibration would mean if I have a big pile of forecasts, I can take all the forecasts to within, I can take all the forecasts where one candidate is predicted, here. I can take all the forecasts where one candidate is predicted to have, let's say, between a 50 and 60% chance of winning, and compare the average proportion of wins that they're forecast with to the percentage of wins they actually had. So if you're calibrated, if you look at, it's like the weather forecast. If you look at all the cases where a candidate's predicted to have a 60% chance of winning, they should win 60% of the time. If you take all the elections where a candidate is predicted to have a 70% chance of winning, they should win 70% of the time, 80%, 80%, and so forth. You can do that. There is on the 538.com webpage, they actually have a calibration graph of all their election forecasts. What you find is that their forecasts are systematically underconfident, meaning that when they say there's a 90% chance of a candidate wins, they actually win more like 95% of the time. When they say it's 10%, it actually happens only about 5% of the time. So their probabilities are kind of too close to 50%, which I'll get back to in a moment. But I'll also say it's very hard to evaluate this, because although they have thousands of predictions, they've only been running their system for like 5 or 10 national elections. So how can you possibly evaluate the calibration if you only have 10 independent events? And the answer is you really can't. It kind of like, so I can say, I think it's silly to say that Biden might get 50% of the vote in Alabama, but like, what does it mean to say that your probability of that event is 0.01%, 0.1%, 1%? Like, it's very difficult to operationalize this. Now, when it comes to making forecasts, I think traditionally we've been concerned about overconfidence. So this is a very unusual case because usually the worry about, in general, the worry is that scientists and policy and analysts understate uncertainty. And generally, there's a lot of motivation for doing that. So, for example, when someone does a study, it's the result is statistically significant and they say they've discovered something. They don't say they're uncertain. Or if the result's not statistically significant, they say the effect is zero, right? So either way, like there's a real problem in science with people overstating certainty, with people like acting as if they know. And similarly in forecasting, there's a lot of pressure. People are always asking me who's going to win the election. And I say, well, here we say that there's an 87% chance. Like they don't want to hear that, right? People just want to hear 100%. Who's going to win what state? So there's a lot of pressure to be overconfident in your forecasting. On the other hand, maybe sometimes there's pressure to be underconfident. So imagine, just for simplicity, imagine that we're supplying 50% intervals for everything. So I'm a forecaster, and this all I do for a living is I make forecasts. I give you forecasts, and I'm going to give you interval estimates for things. So if I give you 50% intervals and 50% of the time I'm right, that's great. I'm calibrated, right? But what if my 50% intervals were all a little bit too wide and they were actually included the true value 70% of the time? I might look even better because that means I'm right 70% of the time. Well, not really, right? Because I mean, like the whole point is a 50% interval should contain it 50% of the time. But really, you have to look at what the loss function is. So as a forecaster, if I were supplying 50% intervals, every time the outcome occurs inside the interval, people think, well, hey, I guess this forecast was okay. Every time it's outside the interval, then it looks like I got it wrong. So there's a motivation for me to make my interval wider. Well, in that case, why don't I make it really wide? Well, at some point somebody would notice. Also, in addition, there is a motivation for a forecast to be informative. So of course, the only way you can get your 50% interval to have 70% coverage is to make it really wide, and people don't necessarily like a wide forecast. And I say all this not because I think anyone is like consciously manipulating their forecasts, but rather incentives matter, right? And there is an incentive for a forecast to appear informative, but there are also incentives for people to make their forecasts extra wide so as like to not miss anything. It kind of depends on what the forecast is being used for. Maybe let me pause now here because I think that was most of what I wanted to say. And I feel like there are different dimensions we could go, so it might make sense at this point for people to ask questions or give comments.
So I'm just going to ask a question. It seemed like in the last election, there was a lot of surprise with respect to polling data and the outcome of the election. Was there something that was significantly peculiar about that particular election with respect to earlier national elections?
When you say the last election, do you mean 2016 or 2018?
The last presidential election.
Okay. Yeah, what happened? What happened in 2016 was that there were a bunch of state polls that did not adjust for education, and polls do generally oversample more well-educated people, and that was a bigger factor, a bigger predictive factor among white voters than in previous elections. So this not adjusting, a lot of national polls have always been adjusting for education, but a lot of state polls, like they don't always do all these steps. And it had not been such an issue in previous elections, but it became more of a big deal in 2016. Now so that is something that happened that was new. Now, going forward, how have we as a community addressed this? So first, pollsters are more aware that they should adjust for education. Second, we're aware of what the pollsters do adjust for, and if they don't adjust for education, we might not use their poll at all. Third, there are some pollsters who also adjust for party identification, And we, as I said, we use that as a baseline. So when the polls that adjust for party identification, we treat as having zero bias, except for a national bias term, like all the polls could be off by a certain amount. But we basically treat them as our baseline. So if that's why when we went back and fit our model to 2016, like it's not perfect because it doesn't know what direction those polls are biased in, like they were wrong, but it allows for it, so it puts less. So it takes, if you have a state with a bunch of polls like that, it makes more use of the national polling. Yeah.
So also when you're sampling a 5,000 dimensional space, as you do in your model with Hamiltonian Monte Carlo methods, is there some sort of convergence checking that you're doing, or how do you know sort of when you're done there?
Yeah, well, you start, we have like 4 chains on our, we have like 4 processors on our laptop. So we start from 4 different places, and then the chains move around and we run it. I mean, a lot of it's just kind of experience, but I think the default is to do 2,000 iterations. And wait a second, there's other people in our apartment doing stuff like opening doors. Yeah, we start from different places, and then we run it for a couple thousand iterations, and then for each variable we can compare the variance between and within the chains. And when the variance between the chain, if you haven't mixed, then the variance of all the chains mixed will be larger than the variance of the individual chains. So that's all done automatically. We have a paper from 1992 on that, but we actually have improved the method. So we have a new paper that came out. We're using the newer approach.
Great.
But yeah, that's the least of our worries.
Okay. Do we have any other questions?
I have a question.
Sorry, let me throw one more thing to get mildly technical on this. So this is a hierarchical model, and you do sometimes have convergence problems with hierarchical models when there's a lot of uncertainty about the group level variance parameters. And one way that we resolve this is to put informative priors on the group level variance parameters to bound them away from 0, which avoids some of the worst geometry issues.
Thank you. Misha?
Yeah, thanks. So my question is, how does our voting system take place in these models? So for instance, you could imagine, we could go to go and vote with a different voting system for our presidential candidate, and that would make a difference in the outcomes of the votes. Is there some way of accounting for that and understanding the effects of our voting system through this model?
Well, we don't model the kind of endogeneity of it. So like, we're assuming that some people are going to vote and some people aren't going to vote, and we have, I mean, the model for turnout is fairly simple. So we're not saying like, oh well, if they counted all the votes equally, then more people in New York might vote because there's a reason for us to vote for president. I mean, there is some evidence that turnout rates are higher in swing states than non-swing states, but not by as much as you might think. Like voting is like something that people just pretty much do or they don't do. So we have not modeled, so we don't model that kind of thing. And so we do, I mean, we do figure out the probability that either candidate would win in the popular vote or the electoral vote, and you can compute things like that. So that we do, but yeah, we don't have a kind of second order model which would say if the voting system is different, then they'd be campaigning differently, and this would be different and that would be different. There have been studies, political scientists have done surveys of non-voters, and it's funny because traditionally you'd say, well, if everybody voted, that would help the Democrats. Then in the 90s, there are some studies and they said, actually, if everybody voted, it wouldn't matter much. It would only change the election outcome by like 2 or 3 percentage points anyway. It's like funny, 2 or 3 percentage points, that would make a big difference. But if you think about, they were doing this stuff in the 90s. So the previous elections had been 1996, 1992, 1988, 1980, 1984, and 1980. None of those were within 3%. There's a series of non-close elections where it wouldn't have mattered. Since then, we've had several very close elections. So yeah, so the indirect effects are large, and that comes, I mean, there's a lot of things that we're not modeling. I mean, it's kind of a crude model, and you really would have to look at separately, like things like vote suppression. Just, that's not in there. And that can make a difference in a close election.
Other questions? So just one thing that jumped to my mind, you said that you had predicted Biden with 99%, and then you thought that was a little bit too high, and then you felt that 97% was okay. And to me, that seems like a very tight margin there. And was it just that pushing away from probability 1.0 just a little bit made it seem okay? But...
I mean, it is kind of funny because, like, there has to be a 99% chance somewhere. Like, if we don't, okay, so we don't say he has a 99% chance of winning the vote, but we still say he has a 99% chance of winning more than, here, let me look. We still say he has a 99% chance of winning more than, say, 48% of the vote, right? Or 49%, right? So there's somehow nothing magic about that 50-50 barrier. Like, at some point you have to bite the bullet and say you're 99% sure of something. I mean, otherwise you end up being like those 538 people who say that, like, Biden could get 55% of the vote in Alabama, right? Like, you somehow, like, you can't have it both ways, right? You have to, if you really don't want to be overconfident, that means you have to at some point draw the line and say this is it. So yeah, it just seemed, so I agree, like, it's not that different. I think that it's like, if you talk about, like, as an estimate and a standard, and I think it was like we had an estimate, it was something like we had an estimate of 54% and a standard error of 1.5%, predictive standard deviation of 1.5%. After we fixed the model, it was like an estimate of 54% and a predictive standard deviation of 2%. So, like, it actually is different. Like because it's in the tail, like 1% tail probability and 3% tail probability, it's not nothing, right? I mean, which I guess being at Cornell, it's so hard to get into Cornell, right? So, like, you're admitting those 1% students and not the 3% students. So it's something.
That's a good point. I think Austin Benson has a question. So, Austin.
Yeah, hey, I'm curious if there's particular types of data or types of polls that you wish you could have access to, or you wish could be run, that would help the models.
Well, I'm interested in polls where they ask people, not just who do you plan to vote for, but how are your friends and neighbors planning to vote. I think a lot could be learned from that. So it's interesting. A few years ago, some people noticed that if you look at polls asking people not who do you plan to vote for, but who do you think is going to win the election, that was a better predictor than who you plan to vote for. And there was kind of some BS about this, because they were like, oh yeah, that's because if you ask people who they're going to win, who you think's going to win, it's like you're asking people about their social network. And I think that's like bogus. I think really what matters is if you ask people who they're going to think is going to win, then they're basically repeating what, like, forecasters in the news media have said. So of course you can predict better because of that. That's really not such a big deal. But then it made me wonder, like this idea that what if, don't ask people who do you think is going to win. Like you should, in general, when you're doing surveys, you should treat survey respondents with respect. Like, ask them something that they might know, right? So ask them about their friends and their neighbors. It seems like there's so much you could learn from that. like, in addition to like maybe somehow getting a election forecast, you can also learn about the political views of people who disagree with their friends in politics. And for a while, I've been saying about survey research has a very atomistic tradition, where you ask people about just about themselves or just about their families. There's not a lot of survey research where people ask, say, tell me about your friends. It's often like a trick kind of thing, right? Like there's a famous survey where they ask people, like, college students, like, do you cheat on exams? And then they have another question, does your roommate cheat on exams? And of course, the roommates cheat at a much higher level than people cheat themselves. It's funny, roommates, they're the worst, right? No, so that's like a big joke. It's like, okay, so there are these trick questions you can ask to get around like issues like that, like how do other people take drugs, so forth. But what about taking it seriously and saying that we can actually use surveys to learn about the social network? Now, often that's done the other way. There's something called network sampling that, like, that Cornell researcher David Heckathorn has worked on, where I wish I could get a random sample, but I can't because I'm trying to reach some group that's hard to reach, a small group of the population. So I do networker sampling. And I've been involved in surveys like this. So you find some people of that group, you ask them to refer other people in the group, you do referral sampling, you get these chains of referrals. Then you have to adjust for the fact that people who have more friends are more likely to be in the survey. So you need to do things. And it's an interesting problem that I've like occasionally worked on, although not written anything up on. But there, the idea is that you really wish you could just get a representative sample, but you can't, so you're using the network property. I'm talking about the opposite, which is maybe you can get a representative sample, but you actually want to learn about the network. So to me, I mean, I've been saying this for a long time. I think this is a real growth area for surveys of all sorts. Although what you do with the data is another story. It's not completely clear. That's why I guess people don't do these surveys. But since you asked.
So I think David Minno has a question. So David? Or maybe
yeah,
okay.
Thanks for a great talk. I was wondering if you could tell a little bit about the state correlation visualization that's at the bottom of the page. This isn't something that I've seen in other sites. Not that I'm like staring at these sites all the time or anything. And specifically, could you say a bit about how that's estimated and how it's being used?
Okay, so I'm not thrilled with how it's being estimated, but okay, so here it is. I shared it. So here it's a correlation matrix. So the economist people came up with this clever visualization to visualize a correlation matrix. You can look at one row of the matrix at a time. So these are the correlations with Kansas. So Kansas has 100% correlation with itself. The correlations are all positive by design. It's highest in these Kansas-like states, the darker ones you can see. Now, why is Maine and why is New England seem Kansas-like, and California's not? I can tell you where the data came from, but let me just first say I am not going to like die on the hill of this particular correlation matrix. What's kind of important is that the correlations tend to be high. Let's do another state, like here's New York. So New York has relatively low correlations with a lot of states, but it's happens to have a high correlation, well, of course, with the states neighboring New York, like New Jersey and Illinois, some other liberal states. Here's you do another one, like here's Illinois, which has a high correlation with New York, of course, and we could do California, which it has high correlation with New York and New Jersey and also these southwestern states. Now, the actual correlation matrix, I'll tell you all, but only if you promise not to like tell anybody else, because it's kind of embarrassing. So what we did was, I'll blame him, Elliot did, was he took a bunch of variables, like he took like 10 state level variables, which are like election returns, some economic variables, some demographics, put them in a correlation, and then just basically created a correlation matrix out of them. Then the negative correlations he set to 0, and then we added a constant to the entire correlate. Then we made that into a covariance matrix, and then we added a constant to the entire squared covariance matrix, to every element, not just the diagonal, to every element, which has the effect of increasing all the correlations. And then we set it so that the average correlation was something, which I don't remember, like 75% or 50% or something. I can't remember. So and I'll explain like why it was hard to do, but just like the motivation for it. So it goes, remember, it goes into the model in a few places. It actually goes into the model because our fundamentals-based forecast is at the state and the national level. So we allow for uncertainty in that. The most important place I think it goes in the model is for this time series, because remember the time series is this key bridge between the poles and the prior, which is the fundamentals-based forecast. But it also comes in, even on election day, it still matters. So on election day, you don't need the time series anymore, but you still have potential errors, polling errors, systematic errors in the polls. So we also use this covariance matrix for the correlation matrix for the systematic errors in the polls. Now, how can we use the same correlation matrix for all three? I don't know, like what are we gonna do, right? So I think the right thing to do conceptually would be to fit this, we are calibrating the model, fitting it to past data. You would fit it to past data and then use the covariance matrix of the errors, or you'd kind of estimate it. But I think when we were doing that, it was, I don't know, like there were reasons why we weren't thrilled with that, looking at the state level errors, because you don't have a lot of past elections. And then also my collaborator felt like it's not just that, like if you have states with similar demographics, you kind of expect them to go similarly. So we wanted to have that. So then, once you have the general correlation matrix, there's two things you need. One is how highly correlated are kind of random states with each other. So first, I want to say all the correlations are positive by design, and I think that makes sense in the sense that, like, if you just told me nothing else but Biden's doing better in state X than predicted, how is he doing in state Y? I think he'd be doing better in state Y. Like, I don't think there are any two states where I would say, oh, Biden's doing better in Montana. Well, geez, in that case, I think he's going to be doing worse in state X, right? Like, I don't think that would be the case. Like, that doesn't make sense to me. Like, you could imagine a situation where you could really gain votes in one place and win the other. But I think in general, I wouldn't expect to be seeing that. Anyway, so then how high these numbers are is basically ends up being how high we want the state errors in the relative to the national errors. So the higher the correlation is, that if the correlation is really high, it means you can have moderate state errors and get a high national error. If the correlation is too low, then if the correlation is too low, then you'll either have moderate state errors and a tiny national error, or you have to make the state errors huge. So I think what happened with that 538 forecast is their correlations were too low. And so therefore, in order to get reasonable national errors, they needed huge state errors, which is why their state intervals were so wide. And we had an exchange with the 538 people, and they said, no, that's not true. We have high correlations, but if you listen to it carefully, look carefully at what they said, they have high correlations, but then they add error terms after they have the high correlations. So the high correlations they specified aren't their final correlations. They're the correlations before I think they added independent error terms. But I'm not actually trying to like put them down. I'm actually just saying, I mean, I already talked too much. It's like kind of a mess is what it is. Like we're putting this together and I'm not like 100% thrilled. And we were like under the gun trying to do something reasonable, and like a lot of choices get made there. But yeah, I do like this visualization. I mean, I don't know what really to do with it. Like, how could someone evaluate it and say, well, geez, this is, I guess, you know, it has a certain face validity, right? But that's kind of circular, has face validity because these are literally based on variables that we know. So there you go.
But I would think you would want to have symmetry. Did it look like New York didn't, New York correlated with Florida, but didn't correlate strongly with California, but the converse, like Florida correlated with New York? That seemed unusual.
Well, the two-way, oh, it's a symmetric matrix. I mean, here's New York. So Florida's at 53. So if I go to Florida, then New York's at 53, right?
But
So
go to California. But California then puts New York at 56.
Now I go to New York and California's at 56.
Oh, okay. Sorry. The contours just didn't quite look right. Or the coloring. I think Mike Liveright had a question.
I call calibration. And I think you discussed it a little bit. And I was thinking that the Good Judgment Project tries to take something which is a lot mathematical. I was thinking maybe we could set up incentives so that a betting model could lead to whether a person was well calibrated as they were making money or losing it, that type of thing.
Well, this is really weird. So I've talked to a lot of people about the betting market. So a few months ago, we came out, The Economist, with our election forecast. We were the first people. And I noticed that we had Biden at like 87% chance of winning, 88% chance of winning. And meanwhile, the betting markets like Betfair and things like that had Biden with like a 60% chance of winning. Now, this suggests like you can make money by betting on Biden. In fact, you can make money in two ways. One, you could just flat out bet on Biden and make money and make expected dollars. I blogged on this. Or you could bet on Biden and the confidence that eventually the odds would shift towards Biden as the betting market started to wise up and respect the forecast, and then you could cash out. So one way or another, it should work. I did not bet money on Biden at that point. Now, why didn't I? Well, for one thing, I don't quite know how to do it, like from the United States. Second, you can't bet a lot of money. Like these are not, like you can't, like it wouldn't be enough money. Like I wouldn't make a lot of money. It wouldn't be worth it for that point of view. The reason to do it would be as a kind of statement. Like I could blog about it, write it in the paper. Like we put our money down. I would have a story to tell you, right? But then I felt a little bad because all the information is public. I mean, I really wouldn't have wanted to bet before The Economist released the forecast. I mean, that would be like, that would be kind of unethical because the forecast could shift the odds. But like, I don't know, I felt like I'm an expert in political science. It seems kind of weird to be like making money off of some poor schlubs, like it seemed a little odd to do. So I didn't want to make a bet. Anyway, I checked like a week or two later, and indeed the odds had shifted toward Biden, although not as much as we thought they should have, but they shifted. So I thought, okay, well now I understand, like, the bettors weren't paying attention and now they are. But then a couple months later, Trump and Biden were even in the Betfair odds. Like, even though we had Trump at, we had Biden at 80. Now, I thought about this, okay, we had Biden at 85% or whatever. I think at one point it was down to 80%. We write about this in our paper, but like, the difference between 80% probability and 88% probability is actually kind of undetectable when it comes to the actual predicted vote share. You move its predicted vote share from 54% to 53%. It does all sorts of things to the odds. But it was, so I could say if we have Biden at 80%, I could see how someone might only want to give him 70% because he'd say, well, there might be a rigged election or like, who knows. But 50%, where is that coming from? So I don't know. Like, so the answer is I would not want to leave it up to the bettors because I think the bettors, like, I have no idea what their motivations are. But that betting markets, setting aside all issues of betting markets, I'll just also say that I think it's hard to have betting markets, even if they were working as they should, it's hard for them to kind of keep the forecasts honest because the correlation in the results. So although I think it's ludicrous to think that Biden has a serious chance of getting 50% of the vote in Alabama, if he, like, I guess, like, it's hard to know even how to evaluate such claims. Like in 100 elections, like that would take 400 years, right? Like it's somehow based on my understanding that he's getting thrashed in the polls in Alabama. People in Alabama don't like Democrats. Like how do you like put all that, ultimately it has to be part of the model. So I think it's just very challenging with the calibration, that's all I can say, because you only get one election. You don't have 50 independent elections.
Great. Well, I think with that, we'll leave it here. We're at the end of our time, and I just wanted to thank Professor Gelman very much for a very interesting talk, and invite everyone to the virtual reception that follows. And so thank you very much.